All right, good morning. Hope you're all well. Um, so we're currently going to be finishing off chapter 5 today. Thursday's lesson was going to be a revision class, and then Friday was going to be the test. So Thursday, we're just going to carry on with chapter 6. So inverse functions. So earlier on when we mentioned one-to-one functions, I told you that the reason that we need them is to be able to work out what an inverse function is. So I wouldn't worry too much about this page at the moment, because we're going to go into that in more detail. But basically, it's about the range of one part of the function being the same as the domain of the other part of the function. But like I mentioned, we'll look at that in more detail. Let's look at a simple one. So we've got these 1, 2, 3, 4, 5 coordinates. And the first part of the coordinate is the x coordinate. The second part is the y coordinate. So if we use the function notation, when we have this point here, the point 1, 2, the point 1, 2, basically what we're saying is when x is 1, y is 2. Similarly for the point 3, 4, what we're saying is when x is 3, y is 4, etc. If we do this on the other way around, this is what we're saying for an inverse function. We're saying, okay, for this point here, if y is 2, then x is 1. So we're just going backwards. So these two are just the inverse of each other. Hence, they're called inverse functions. So the inverse points for this function here are just the same points written in the opposite order. So 1, 2 becomes 2, 1. 3, 4 becomes 4, 3, etc. Pretty simple. You've got to get, if you can understand that concept, you should be okay for the rest of this topic. So the domain is the x coordinates, or the x coordinates 1, 3, 5, 6, 0. We went through this in previous lessons, and the range is the y coordinates. So if we want to write them out, the domain of the inverse function, so the domain of the inverse function is the first coordinates of the inverse function. So as you can see, the domain of this one is the same as the range of that one. And the range of this original function is the same as the domain of the inverse function, which what I mentioned in the previous slide, but hopefully this will make it a little bit more clear. So visually, we can look at these things visually. So here's the graph of any function, so any function f, and here's the inverse function. Okay, the coordinates of this point here are yx, the coordinates of this function xy. And you can see that this line here, the line y equals x, is kind of like a mirror, and it reflects the two functions. So the reflection of an inverse function is in the line y equals x. But I'll show you lots of examples of that. And don't forget to tell whether or not a function is one-to-one. We use the horizontal line test. So some examples. Define the inverse function of this function, 2x minus 3, and sketch it. So sketch both graphs on the same set of axes. So this is the crucial bit here. It's the fact that the x and the y are interchanged. So if we have a function y equals 2x minus 3, the inverse function will have the equation x equals 2y minus 3. So basically we're just swapping the x and the y around. It's not as simple as that. We have to do some rearranging. So when we have x equals 2y minus 3, we have to rearrange that. So we add 3 to both sides, divide by 2, so we get the function y equals half x plus 3. Now we've just got to check our domain and our ranges. So because the original function has a range of f, and so the domain is f as well. But we'll look at some later on where that isn't the case. So if we sketch them, here is the graph 2x minus 3. Here is the graph half x plus 3, and we can see if we have a dotted line, the y equals x, they are a reflection of each other. They're a reflection of each other in the line y equals x. There you go. Another example. So we're going to draw the new function, state its domain and its range. So here's the original function. We've gone from function notation to y equals notation, just to make the algebra a little bit easier. It doesn't make any difference, it just makes the rearranging easier. So we got x equals y over 3 all squared. We've just rearranged it, yeah? Swap the x and the y's around. Looks like the algebra might be a little bit more tricky. So you've got to square root both sides. And don't forget, when you square root, so we square root and then we times everything by 3. Don't forget, when you square root something, you get a plus and a minus. And often when we're drawing a graph, that means it's above the x-axis and below the x-axis. But because the domain of this function goes from 3 to 6, it means that the range will go from 1 to 4. So where does this 1 to 4 come from? So let's look up here. If we've got 3 to 6, so the domain of this one is from 3 to 6. So if we substitute in when x equals 3, we get 3 over 3 all squared, which is 1. And when x equals 6, we do the same. 6 over 3 all squared equals 2. So that's just x over 3. If x is 6, and we get 4. So that's where our 1, 4 comes from. So we can see the domain goes from the domain of the original function. So here's our original function, f. The domain goes from 3 to 6. And our domain goes from 3 to 6, and our range goes from 1 to 4. But on the inverse function, that's swapped around. 1 to 4 is our domain, and 3 to 6 is our domain. So our range and our domain swap around. And don't forget, we've still got that beautiful reflection through the line y equals x. We can see that beautiful reflection on both sides. There you go. Okay, here's another one. And look at this one. So we've got a domain here, of the original function of 1 to infinity. So we write it out, x and y swapped around. Then we do some rearranging to get y equals 1. Don't forget, whenever we square root something, we get a plus and a minus. So, but because the range of the new function has to be the domain of the original function, the domain of the original function is 1 to infinity, so all positive numbers, yeah? So the range of this one has to be just the positive side. So we're not, when we've got our plus or minus, we're not including the minus, we've just got the positive bit, So here's just some examples. I've just gone onto Desmos and drawn some. Now, Desmos is cool because I don't have to do any rearranging. I can just type y equals 2x minus 7, and then in this one I can just type x equals 2y minus 7. So it automatically does the inverse work for me. And I've just drawn the line y equals x just to help us with the visual. So we can see they're reflections of each other. This one here, a little bit more difficult to see. So this is really quite difficult to see. So here's the line. Here's one function, and they're a reflection of each other in that line y equals x. So if you can see that, you're much better at visualizing than I am, because I'm finding that very difficult to visualize. I've seen it so many times, so I know it is, but have a look at it really carefully and spend some time trying to understand why they're a reflection of each other. That one there, really easy to see, isn't it? So that's a perfect reflection in the line y equals x. That one there again, looks kind of cool, doesn't it? Beautiful reflection in the line y equals x. So we just swapped the x and the y values around. Inverse functions. Okay, functions and modeling. So this is kind of like our worded question section where all the marks are. So the maths will often be a little bit easier, but the actual developing the maths and coming up with the formulas is the tricky bit. So a book club, I'm sure you're all a member of one. Membership fee of $60, and each book purchase is $10. Construct a cost function and then sketch its graph. So your notation, coming up with this, so you don't necessarily have to come up with the same notation as this or using the same letters. Makes sense to me to use C for cost, and N is often used in maths for the number, isn't it? The number. So this is the number of books purchased. So it's $60 plus $10 for every book you buy. So if you draw the graph, it starts off at 60. For every book, it's 10, so that's 70, 80, 90, etc., etc., etc. So don't forget, if we're looking at the domain, we're thinking about things like domain and range. So when you're in your head, I want you to be thinking about these sort of things every time you're doing this sort of question. So it's all natural numbers, so it's just counting numbers, and it does include zero. I don't know if anyone's ever been there. Yeah, they make a lovely burger in that country. Lovely stuff. So if we're going to sketch that graph, what sort of graph is this? Shout it out loudly. hybrid function or piecewise. Yep, I think I could just about hear you. So if it's up to, so if the letter is less than 50 grams, it's going to cost 70 cents. So if it's 10 grams, 20 grams, 30 grams, 40 grams, 50 grams, does it include 50? It does include 50. So if it's exactly 50 grams, it'll cost 70 cents. If it's between 50 and 100, it doesn't include 50 because we know that is in this category, but it does include 100, $1.15, etc. Now these graphs look a little bit weird. So don't forget we got that not colored in. So obviously we cannot have a letter that is 0 grams. If it's 50, it goes into this one, doesn't it? If it's 100, it goes into this one. So that's what, and you've seen them anyway, that's what a hybrid function looks like. We're thinking about our domain and ranges, aren't we? So our domain and range, anything up to 500. So from 0 to 500, look, we've got a round bracket because it can't include 0, and we've got a square bracket because it can include 500. And our range, so our range is kind of really, there's not it's actual thing here. So that one is actually 70. That one is actually $1.15. So we just actually list them out. Because there are only 4 of them, we can list them out. So these enclosures, the paddocks, the squares that you have to create, if you remember that last test, this is going to be a theme throughout the rest of math methods in year 11 and year 12, and it's either going to really, really annoy you, or you're going to think, yeah, I can do those. I've done so many of these. I know what I'm doing. So there's we're going to construct it. So if we say, again, it says in terms of its length L. So let L be the length of the enclosure. So there's the diagram. Right, okay, so if the length is L, because it's 12 all the way around. So that plus that plus that plus that is going to be 12. So if you think about the width is the whole perimeter, take away 2 of the lengths, and because there are 2 widths, we have to divide by 2. So the width is 6 minus L. So the area, length times width, so it's length times width, we've got a quadratic function. So there it is, I've graphed that quadratic function. That's something you probably should be quite easily be able to do. You can use your graphics calculator if you're allowed to, but that's something that you should know how to do. What does it say? So in terms, find its area A in terms of its length, done. Sketching a graph, done. Find the maximum area. We can see that the maximum area looks like to me that it's 9 square meters. So the maximum area is 9 square meters, and that occurs when the length is 3. So if you think about it, the maximum will always be halfway between the 2 intersects. So halfway between 0 and 6 is 3. So visually you can see that our maximum is 9. And okay, we've looked at our domain. So our domain is 0 to 6, and it does include 0, and it does include 6. And bizarrely, if the length is 3, 6 minus 3 is 3, so that is actually going to be a square. A square will give you the biggest area. Some work for you to do. So as I mentioned, on Thursday we were going to have a revision lesson, and then on Friday we were going to be starting chapter 6. So we'll be starting chapter 6 on Thursday's lesson. So if you're already up to date, then you just got this bit of work to do, and as you're at home, you've got loads and loads and loads and loads of time. Any questions? Whack it all on Google Classroom, and over and out.